Good evening all. Just give me a second. Yeah, I guess the screen is visible. Maybe we can wait for a minute or a couple of minutes to see if someone joins, or we can get started. We'll get started with question number 1. So question number 1 essentially asks, gives you two differential equations. However, here we have two different variables. It's a one-dimensional equation, but we have two variables, y comma z, and they are coupled through the differential equations. The objective is to discretize the cells for such cells and then make the forms amicable to be solved with TDMA that we learned in the lectures. So let's write the equations. So the boundary conditions are all similar except okay. So we have y by del x square plus z equals 0 with y of x equal to 0, 0, and y of x equal to 1 as 1. Also we have del square z by del x square plus y equal to 0, z of x equals 0 equal to 1, and z of x equal to 1 equals 0. So it's a straightforward equation. So you have 1D diffusion equation, and this will be constituting your source term. So you have your domain x equal to 0 to 1. So the question asks you to solve with 3 cells. So we will discretize in 3 cells. We have 1, 2 and 3 cells. So this is cell 0, cell 1 and cell 2. Now let us discretize equation 1. For equation 1, cell 1, we have, if we discretize it, so the equation will be y2 minus y1 by delta x minus y1 minus y0 by delta x plus integral of z dx will be z calculated at the center node of that particular cell times delta x equals 0. So this gives us delta x square. Similarly for this is for the y equation, and similarly we have a z equation. So for the z equation, the equation will be 2 times z1 z1 equals z2 plus z0 plus y1 times delta x square. Now for cell 0, we have y1 minus y0 by delta x minus, for the left hand cell it's y0 minus the initial condition at x equal to 0 is 0, and it's just a half cell, so delta x by 2 plus you have z0 times delta x equals 0. So this gives us 3 times y0 equals y1, and then we have z0 times delta x square. Now when we write the equation same for along the y direction, for the z equation we have z1 minus z0 by delta x minus z0 minus the boundary condition is at x equal to 0, the value of z is 1. So we have 1 over delta x by 2 plus y0 delta x equal to 0. So this gives us 3 times z0 equals z1, and we have a y0 times delta x square and then a 2 coming from the source. Similarly, for the last cell we'll be having a similar equation here, so it will be 3 times y2 equals, it will be in terms of y1, and then we have a z2 times delta x square and then a constant term, and along the z direction will be along z equation will be 3 times z2 equals z1 plus we will have a center node y2 times delta x square. The boundary condition is 0, so we don't have any other additional terms. So now here we have 6 equations. We have 6 equations and 6 unknowns, and as you can see, like we cannot directly apply the TDMA because the first set of equations, so maybe I'll just number them. The first set of equations are different, has a z1 term, and the second set of equations also, so like the equations for z has the contribution from y and equations of y has a contribution from z. So the direct application of TDMA is not possible, so we need to adjust these equations so that we will be able to solve them. So what I will do is we will club equations 1 and 2, so like we will club these two equations, these two equations, these two equations. Say suppose we'll take 1 and 2, equation 1 and 2. What we have is I'll write it in a different way, slightly different way. So if you write it in the matrix form, it will be, can be written as, or maybe I'll write the original equations and then slightly change them. So we have a y1 z1 equals, we have a contribution y2 z2 z2 y0 z0, and then we have g1 times delta x square and y1 times delta x square. We have a 2 here and then a 2 here. So if you take these two equations together, if we can kind of rearrange this in a slightly different way, so we can write this as, if you put a matrix here, 2 0 0 2, and similarly the contributions are 1 here, so we can put an identity matrix. And similarly for contributions for y0 and z0 are also 1 0 0 1, plus the last one also can be written. So since we want expressions in terms of y1 and z1, so maybe I'll write this in a slightly different way. So if I write it as y1 z1 delta x square, the first one has a contribution from z1, the second one has a contribution from y1. So I can write it in this particular way. So if you try to expand this, say we expand only for the first row, so we get the same equations back. So 2y1 equals y2 plus y0 plus z1 delta x square, and similarly we'll get the other equation as well. So if I write in this particular format, in this particular way, so what we have is we can write this as some A matrix times, let this be denoted by some vector u1 equals, this entire thing we'll write it as B times u2 plus this is our C times u0, and then we have something here which we can treat it as some constant, since these are the values which are of the current unknown. Okay, maybe I can split this as well. So you have so if you see these things, so I can bring this to LHS. So this term over here and this term over here have something in common, so I can just bring it to the LHS side. So I will have 2 minus 1 minus 1 2, oh sorry, so it will be 2 minus delta x square minus delta x square 2 times y1 z1 equals 1001 y2 z2 plus 1001 y0 z0. So if I now define a new vector u as y and z, so what I have is this is something like a times u1 equals b times u2 plus c times u0 plus some d, which is in this particular case this is equal to 0. So now we have our standard form of TDMA, and we can solve using the normal algorithm. So in a similar fashion we can write the other two equations. So this is for equations 1 and 2. Now if we write for equations 3 and 4, so these are my 3 and 4. So it is again straightforward. So we will write it as 3 minus delta x square minus delta x square 3 times y0 z0 equals 1001. So maybe we will call this as a1 b1 c1 d1 times y1 z1. But in addition to the previous one, now we also have 0 and 2 here. So here we have something like a0 u0 equals b0 u1 plus d0. So this is equation number 7, this is 8. So where a0 is this matrix, b0 is this matrix, and d0 is the corresponding matrices. Similarly we can do for the last set of equations 5 and 6. So here again it is straightforward. So you just write 3 minus delta x square minus delta x square 3 y2 z2 equals an identity matrix times y1 z1, and then we have 2 0. So here again we have something like a2 u2 equals b2 u1 plus d2. So now we have equation 7, 8, 9, something like so it's of our standard form a0 u0 equals b0 u1 plus d0, and then we have a1 u1 equals b1 u2 plus c1 u0 plus d1, and then we have the last equation a2 u2 equals b2 u1 plus d2. Now this is in our standard TDMA. So once we have reduced it to the TDMA form, we can apply the normal TDMA algorithm. But the only difference is previously all these AI, BI and CI are all scalars, but now we are having, like in our particular case, these are matrices right now. Previously they were actually scalars. That will be the only difference, but the approach is again the similar. So you just define P0 as your division will be replaced with your inverse, so B0 by A0. A0, we have the value of A0 here, so this is our A0 matrix. Then we can invert this matrix. It's just a 2 by 2 matrix, so you can invert it and then you will get the value of P0. Similarly, your Q0 is d0 by a0. So once you get this, you can start your iterations. So your pi will be bi by ci minus a times pi minus 1. It's like by division operator is replaced with your inverse inverse matrix inverse, and qi will be replaced by once you iterate it, you get the last final value will be your u. Last value is, say, in our particular case it is u2, so u2 will be equals q2, and then you apply the reverse where ui will be equals pi times ui plus 1 plus qi. Like the remaining every algorithm, the previous algorithm is same here. The only difference is, unlike the previous one, now you need to, instead of dealing with scalars, you will be having matrices here to deal with. That will be the only difference. So that is with the first question. So we discretize with 3 cells, and then
I have a doubt here.
Yeah, sure.
So how did you write that dou square u by dou x square into the algebraic form?
This part.
First, yeah, this one.
Yeah, so when we do the, like, it's just the standard way. So when you try to integrate here, so it will be times dx plus integral z dx. So say this is my west face and this is my east face. So this will be written as del y del x on the east face minus west face.
Okay.
So got it, right? So here you have z1 times that x. So everything is similar.
Yeah, got it.
Yeah. And now we'll go to the next question. So the next one is also a fairly standard question, in the sense it's again the same question. We take a 1D steady state diffusion equation without any source or sinks terms, and we have Dirichlet boundary conditions. The only difference between the previous sessions and this one is now we will be dealing with a quadratic profile. In all the sessions when we were, so maybe I'll just take it up. So the equation is again straightforward. ddx of, so thermal conductivity is assumed to be 1 equal to 0, and we have Dirichlet conditions. Say we have some phases. So this is my P cell, this is my east cell, this is my west cell. Maybe I'll take it a bit more. So we have this as east. Maybe this also I'll extend a little bit. Say this is my west. So what we are saying, when we used to do this for a particular cell, P cell, say for this cell, if I am writing this, so this is my west face and this is my east face. So what we have here is dt dx on the east face minus west face equal to 0. So but what we have been doing till now is how do we approximate dt dx on the east face is we just take a linear profile assumption, in the sense dt dx will be this, we are taking as t east minus tp by delta x. So this is what we call a linear assumption. So we just take two cells and then we approximated the gradient with that particular two cell values. But now what I am saying is this is a case of a linear profile assumption. So what would be the order of accuracy with this assumption?
I think it's second order.
So you are saying it is delta x square. Okay, we'll come to that. So what the question asks now is to do for a quadratic profile assumption. what it basically means is now to approximate the value on the east face, what I'm asking is don't just use the value of each cell but also use the east cell. So we'll be using all the 3 cell values to get the profile assumption. So first take the case of linear profile. So in the case of linear, what we are saying is say your dt dx on the east face is approximated in terms of Tp and Te. So since it is a linear approximation, I am just putting 2 constants a and b, a times Tp plus b times T east, and my objective is to get the values of a and b. So how do I do? So I will just use the Taylor series expansion. So a times Tp and T east can be written as Tp plus delta x times, or since we want in terms of the east face, maybe I will just draw it here. So this is my east face, this is my peach cell, so this is my east cell. So we are considering anyway for a uniform case, for a uniform grid. So your Tp can be written as in terms of the value at the east face can be written as T east face minus delta x by 2 dt dx on the east face, and then you have delta x by 2 whole square 1 by 2 factorial d square t dx square on the east face, and so on, plus the cell centered value on the east face, east cell can again be written in terms of t little e plus delta x by 2. So it will be delta x by 2 dt dx on the east face and so on. So the objective is to get the values of a and b. Now if for the LHS to be equal to RHS, essentially your terms for T should vanish and these terms should add up. So what I meant by that is if for LHS to be equal to RHS, we need A plus B to be equal to 0, and then we also have minus A times delta x by 2 plus B times delta x by 2 to be equal to 1, and we are neglecting all these terms. So this is essentially what you are saying. So we have order of delta x square. So by this approximation we are getting a second order accuracy. So if we solve these equations, so from this we have b equal to minus a, and then we have b times delta x equal to 1, which gives us b equals 1 over delta x and a equals minus 1 over delta x. So this leaves us with dt dx on the east face to be equals to, from our original case, a times Tp plus b times T east. So this is our original approximation in the case of a linear profile. So now this is straightforward. Now in a similar fashion, what we want is for a quadratic profile. So when we take a quadratic assumption, so what I am saying is you express your gradient on the east face in terms of peak cell, the current cell, the east cell, and we take one extra cell, so that is our east. So we now have 3 constants, so we will be needing 3 equations. So the process is again similar. So what we so this is my east face, this is P centroid, east centroid. So we can write it as same equations come, but instead of we will go another step. So we will have T east minus 2 dt dx on the east face, and then we have by 2 square 1 over 2 factorial d square t dx square on the east face, and then we'll get one more term, delta x by 2 whole cube 1 by 3 factorial d cube t dx cube on the east face, plus some higher order terms. Similarly for the east face, east centroid, we have t east plus x by 2 dt dx east face, and for the east we'll have something here. So we have this is another delta x, so we have delta x plus delta x by 2, so that is 3 delta x by 2. So we have t east plus 3 delta x by 2 dt dx on the east plus 3 delta x by 2 whole square 1 by 2 factorial del square t del x square on the east face, and then we have 3 delta x by 2 whole cube 1 by 3 factorial del cube t del x cube on the east face. So now when we write the equations for LHS to be equal to RHS, the coefficient of TE should be 0. So coefficient for TE should be 0. Coefficient for dt dx on the east face should be equal to 1. And the coefficient for d square t dx square on the east face should be 0. And we are neglecting very higher order terms. So this approximation will be of the order of delta x cube. So for from the first equation we have a plus b plus c equals 0. From the second equation we have minus a delta x by 2, or if I just take delta x by 2 to the other side, so we have minus a plus b plus 3c equals 1. So I am just taking delta x by 2 to the other side, so we have 2 over delta x, and then from the last equation we have a plus b plus 3 square will be 9 times c, the remaining everything will anyway be 0. So this will be my set of equations. If we solve these equations, say we'll get something, yeah, we can just take these two. This gives c equal to 0. Did I miss something? I think we may have to go one step further also, because with these three equations you will end up with the same thing again. So if you solve, say this is my 1, 2, 3, so if you take 1 and 3, we will be left with c equal to 0, and in that particular case it will be the same as the previous one. So if we substitute back in 1, we get a plus b equals 0, so b equals to minus a, and then we just take it in step 2, so we get 2b equals 2 over delta x, so which again gives b equals 1 over delta x. So this will be similar to your original one. So it is because of these terms getting cancelled off. Okay, then we will take one more term. So we have del cube t by del x cube on the east face. That coefficient should also be 0. So what will that give? So that has minus a plus b plus 27c equals 0. So if you just take these three equations, say 1, 2 and 4. So we have b plus 27c equals to a, which gives us 2b plus 28c equals 0. B equals minus 14c, substitute back. 13c equal to a, substitute back. We have minus a plus b plus 3c is 2 over delta x, minus a is minus 13c, b is 14c plus 3c, 2 over delta x. So this is minus 11 minus 24c, so minus 24c plus 2 over delta x. This gives c equal to minus 1 over 12 delta x. B is 14 by 12 delta x, and a is 13 times c, so minus 13 by 12 delta x. So now if we substitute this back, what we have is a times tp plus b times t east plus c times I think there is some mistake. So if we substitute this back in equation number 3, what do we get? So we have minus 13 plus 14 minus 9, which is not equal to 0. So which means these equations are not satisfied. So I think we have made some mistake here. So Tp is essentially written in terms of Te, so that is Te minus this, and then T east can be written in terms of plus delta x by 2. And T double east can be written as delta x by 2 plus delta x, that is 3 delta x by 2 times dt dx. Coefficient of T should be 0, and dt dx should be 1. That gives us minus a plus b plus 3c equal to 2 over delta x, and the other coefficient should be 0. So I think we have to stick with the same thing. Okay, I'll get back to the exact expressions. Maybe I'll upload it once the session is completed. In the interest of time, so finally you'll get some expression of this form. So dt dx on the east face will be written as some coefficient Cp times Tp plus C east times T east plus C west times T west, T double east. Maybe I'll write C double east, T east east. So your on the east face it will be some expression of this kind, and similarly on the west face you will have some coefficients. So we will put dp times tp, and you will have something on the west face, west cell and west cell. So what this is essentially means is, now you will have your equations in a slightly different form. So you have ak if your cells are numbered in this way. So if this is my cell centroids, if this is my kth cell, this is my east cell k plus 1, k plus 2 is my east cell, this is my west face west cell, and this is my west cell. So when I am writing in a form that is we have used for TDMA, so your equations will be something like AK TK will be now written in terms of k plus 1, bk plus 1, tk plus 1 plus, now in a, previously we just had one term, now we will have a k plus 2 term as well. So we have ck plus 2, sorry ck, let's not get confused with the notation. So bk tk plus 1, ck tk plus 2 and then these are the forward cells, and then you go in the reverse direction, in the west direction. So that will give you dk times t k minus 1 ek times t k minus 2 plus fk. So previously we just have this term and this term. Now these are this and this are another additional terms that are coming because of your east-east and west-west cells. I'll come, maybe think we made some mistake in this particular form. But the procedure is the standard. You just take the number of cells, you take the coefficients in this particular way, and then you do the Taylor series expansion, and once you get the Taylor series expansion, you equate the corresponding coefficients, like you essentially make LHS equal to RHS, and the leftover terms will be your order of accuracy. So that is the method. So I think that is clear. Method is clear. So
I have a doubt here.
yeah.
So we are telling it as a quadratic profile, right? But anyway, at the end we are getting a linear combination. So what is the significance of quadratic profile?
I mean, essentially your order of accuracy will be increased. That's the only advantage you will get.
Okay.
Yeah, you can try the other way as well. Okay, but that is anyway not the point now. You have seen, like, if you do it in a, like I have done it in a linear combination, essentially because if you do it in this way, the final equations will again be a set of linear equations. We are just solving, like the methods we have introduced are only for linear equations. Now instead you can try it as in terms of, like, currently our format is sin ax plus b. Now you can take the same cell, but then you can define profile something like this, and then get these coefficient values. But the problem with that will be, like, instead of x you will have t, so at square plus bt plus c, something like this. The problem is then you will eventually end up with non-linear equation. So
yeah, got it.
So I've just used a linear form. Yeah. The third question is straightforward. Again, so we have a 2D domain. So these are the set of the general form of equation that you will be getting. So in the last week we discussed about Lyman and Gauss-Seidel method, which is an iterative method. So if I want to use a direct method, so how do I solve it? So the general form of equation is A is A. Phi j will be written in terms of I plus 1 So now if you try to make some suitable transformation such that your k will essentially will be some function of I comma j, such that your g of I plus 1 comma j will correspond to k plus 1, j plus 1 will correspond to k plus 2, I minus 1 will correspond to k minus 1, k minus 2. So if you can define a hash map, or you can just define a dictionary or something in Python as you call it, with this transformation, so the above equation can then be written, and your ij will correspond to this. So the above equation can be written again like ak phi k as phi k plus 1 So this is something very similar to the one which we previously got. So for just like a TDMA, we call this a pentadiagonal matrix. So if you're familiar with linear algebra, so what does your TDMA do is, so you have equation something like this. So when I have something like this, what TDMA does is, if you can write it in a matrix form, you have your phi0 phi1 going till phi n minus 1. Here you have d0 d1 going till dn minus 1. You have something like minus a0, you have b0, so on, and you have c0, sorry, so a0 will be positive and k plus 1, b0 will be negative, minus c0, a0, sorry, a1, c1, b1, and so on. And similarly for the last cell, we will be having cn minus 1, an minus 1. So you will be having a tridiagonal matrix here. So you will just have one diagonal and one super diagonal and one subdiagonal matrices. So this is your tridiagonal matrix. And hence the name TDMA. But now when we have in addition to k plus 1, k plus 2, in addition to k plus 1, k minus 1, we are now having k plus 2 and k minus 2. So now instead of being tridiagonal matrix, it will now be a pentadiagonal matrix. So we'll have a main diagonal elements, we'll have two upper diagonals and two lower diagonals. If write in the standard form. So this is essentially our pentadiagonal matrix. So how do we, so there should be a direct method to solve it. So the idea is again very similar. So we take the original form, so it's general form. So in TDMA we started with to derive this iterative form, we started with the expression like phi k plus 1 or phi k is expressed in terms of k plus 1 and k plus 2. So previously we have just done phi I or phi k is pk times phi k plus 1 plus qk. There just because we have one cell, so it was straightforward. Now we have one more additional one, so we will consider that k plus 2 plus rk. So what we do from this is, now we will substitute back for k minus 1 and k minus 2. So your phi k minus 1 can be written as pk minus 1 phi k plus qk minus 1 phi k plus 1 plus rk minus 1. This is for phi k minus 1, and similarly we can write for phi k minus 2. That will give us pk minus 2 k minus 1 plus q k minus 2, k plus 2 will essentially be k plus rk minus 2. Now we already have the expression for phi k minus 1, so we will just substitute that back. We just group terms together, so we'll have phi k pk minus 2 pk minus 1 plus qk minus 2, and then we have phi k plus 1 corresponding to pk minus 2 qk minus 1, and then we have a constant term. So this is my phi k minus 2. Now the approach is again straightforward. So now we substitute it back in the original equation. So we have ak phi k is bk phi k plus 1 plus ck phi k plus 2. So maybe I'll just give some numbers. So this is 2, this is 3, plus we have dk times equation 2 comes here, equation 3 comes here, plus fk. So the next step is, again, the idea is to essentially write this equation. You compare this, say this is equation 4. Now we compare equation 4 with equation number 1, and we take the we should give different numbers. So this is equation 2, 3, 4 and 5. So dk times phi k minus 1 is equation number 3, phi k minus 2 is equation number 4. So now we compare equation number 5 with equation number 2 and take the coefficients. So first we will take the coefficient for phi k plus 1. Phi k plus 1 coefficient is essentially pk, that equals, so in equation number 5 it will be 1 over ak. So we will just take this. So we will just take the numerator first. So phi k plus 1 has a coefficient here bk, and in equation number 3 we have a coefficient here for k plus 1 term. So we take that back, so that will be plus dk times phi k plus 1 coefficient is q k minus 1, and then we go to equation number plus ek times equation number 4. In equation number 4 the coefficient for phi k plus 1 is pk minus 2 times qk minus 1 whole divided by, now we have to group the coefficients for phi k. So we have a coefficient ak here, and then in equation number 3 we have a coefficient of pk minus 1, so that goes to the LHS, so that is minus dk times pk minus 1, and then in equation number 5 we have a coefficient of this for phi k, so that goes on to the LHS, so we have minus ck times pk minus 2 pk minus 1 plus qk minus 2. So this will be my expression for pk. Now similarly for qk, if we group the terms again, so in equation number 2, so qk are essentially the coefficients of phi k plus 2. So if we group terms, first the numerator, so here we have a ck. In equation number 3 we don't have any phi k plus 2 term. Equation number 4 also we don't have any term, so that is just ck divided by phi k terms are again similar, so it just comes out here. The last one is the constant terms, so we have an rk that includes the constant terms. So in the original equation we have the constant term fk here, and then from equation 3 has a constant term of rk minus 1, so dk times rk minus 1 plus equation number 4 has a constant of ek times pk minus 2 rk minus 1 plus rk minus 2. The denominator is again the same. So now we have expressions for pk, qk and rk. So what we need is to again the starting cases. So what will be the value of p0? So if you see the equations, if you see the original equation for k equal to 0, that is the very first cell. So this is my k equal to 0, this is my 1, 2 and so on. So for the very first cell we don't have any west or west-west, so essentially your d0, we don't have a west cell, so d0 will be 0 and e0 will be 0, and similarly for the last cell we won't have any, or for the k equal to 1, and similarly for k equal to 1 you don't have a west, like when you are here you will have a west cell but we don't have a west-west cell. So essentially what that means is west-west coefficient is e1 equal to 0. So these are from this this is 1, so if you substitute that here, so your p0 will be b0 by, so it will be very similar, b0 by a0. Your q0 will be c0 by a0, and your r0 will be f0 by a0, since d0 and e0 are 0. And from these equations, now you can iterate. So you'll be able to get p1, q1, like you, for any I, you will get pi, qi and ri, and then you keep on iterating till the last cell. For last cells, you just need to remember that for the n minus 1 cell, so if this is your last cell, say n minus 1 cell, this is your n minus 2 cell. So when you are at the I equal to n minus 2, you don't have an east-east cell. So Cn minus 2 will be 0, and for the last cell, both east and east, Bn minus 1 is the east cell, and east is Cn minus 1, both of them will be equal to 0. If you use these expressions, you will be able to get the final expressions, all your pi, q and ri. Once you get all the values, now you use your original expression. So your phi k equals pk times phi k plus 1 plus qk times phi k plus 2 plus rk. As we have seen, when k equals to n minus 1, you have both of this will turn out to be 0. So if you see the pk expression, your b is essentially 0, and you won't be having any other terms. So in that particular case, for the last cell, you will have phi n minus 1 will be equal to rn minus 1. So once you know this, now you again iterate back using these equations. The idea is again very similar to TDM. The only difference is now we have one more additional term, k plus 2. So in addition to east and west, you will be having east, east and west, west cells. So this is the direct method. So instead of using a line by line plus line by line TDM, you can use this pentadiagonal algorithm to solve the system of equations using a direct method. I think this is clear. I hope this is clear. So we'll go to next question. Question number 4 is an unsteady diffusion equation. So we have the initial conditions. Okay. So at one end is held fixed at 0, and at the other end is an adiabatic. Initially it gives you that the profile is linear. We have to discretize the equation using Crank-Nicolson scheme, and then we will solve and march time till the value is equals to 0.5. So the equation is straightforward. Del t del t equals del theta del t equals del square t del x square. It is given like initially the profile at x t equal to 0 is linear, and as time progresses up, you have at x equal to 0 is Dirichlet condition always, and del theta del x at x equal to 1 for all t equal to 0. This is adiabatic condition. So as always, this is my x equal to 0. So this is say x equal to 1. If we first discretize it, so we first take the faces, and then we consider the cell centroids. Say it is a uniform grid. So how do we start with? The discretization for space is again straightforward. So your terms will be, so how do we start? So we have, now previously we just had a dx term, now we will also have a dt term. So we will have two integrations, one for the dx, say we are doing for this particular cell. This is my west face, this is my east face. So we have west to east, and also from, so I am just writing 0 to delta t instead of t to t plus delta t will be equals dt. So I'm just taking this inside and write this as this. This can be again written as del t del x on the east face. So before dealing with the spatial temporal one, we will just see this one. This is again straightforward. Delta del x on the east face will be, if you use linear approximation, by delta x, and then you have s theta west by delta x. So this is again straightforward. Now what we are, how do we do this? This time over here, we will replace with the mean value. So this will be theta p times delta x. So now what I have is 0 to delta t. So LHS is straightforward. So you have del t of theta p delta x times dt. RHS is something we need to think about. So we have a theta east plus theta west minus 2 theta p x times dt. So now before solving this, the approach asks you to use Crank-Nicolson. I think we stopped somewhere in the last week regarding discussion on your time discretization. So we can use either an explicit or an implicit method. So Crank-Nicolson is essentially an implicit. What I mean by implicit is, so you have some equation of the form dx dt equal to f of x. You can solve it in several different ways. The classic or the standard way is, say, use Euler method. Euler method is where you approximate dx dt as, say, xn plus 1. N is your indicating your time step, minus xn by delta t. You can approximate dx dt as this. Now for the value of f of x, we will assume the current step value. Xn is the current step value. So from this you can directly get the xn plus 1 value as xn plus delta t times f of xn. This is forward Euler. Alternatively, you can do it in a different way, where you will write this as xn plus 1 minus xn by delta t, but instead in an implicit method you can write this as xn plus 1. So now what happens is, now you have to solve your equation xn plus 1 equals xn plus delta t times f of xn plus 1. This is completely implicit, fully implicit method. In this case, what happens is, now we have to solve. It is not a straightforward equation like previously. Since xn plus 1 is also an unknown, you need to solve this using some other algorithms. Say, this is essentially what we are saying as a nonlinear one, if f is nonlinear. What Crank-Nicolson does is, it's a kind of a semi-implicit, where you just take contribution from both of them, like half of it. So you will consider the same. So it will be xn plus 1 minus xn by delta t. However, on the RHS, you will consider both at the current time step as well as the next time step. So now you have to solve your equation. So this is something that is known. And this is something that will contribute to your nonlinearity. So this is a kind of an implicit method, since we have xn plus 1 is an unknown, and your RHS is also kind of expressed in terms of xn plus 1. So how do we solve this kind of equations is, we use some kind of an iterative method called Newton-Raphson. I'm not sure previously if you are aware of Newton-Raphson. Maybe I'll just go.
Yeah, I know.
Okay, you are conversant with this. Now, anyway, for the benefit of others, just to give a brief overview, just to give a brief idea. So if you have some function g of x equals to 0, and you want to find the value of x at which, find x such that g of x equal to 0. If you have some problem of this, what Newton-Raphson does is we will take an initial guess, x0, say x0 is my initial guess. So now what we do, we'll take normal, so we'll take g prime of x, that is your derivative, as can be expressed as g of xn minus xn minus 1 by xn minus xn minus 1. So what we expect is, since we are at, will come in a backward fashion, so suppose your xn is a root, this is my final root or value at which g of xn equal to 0, what will be my previous value of xn minus 1. So what we are saying now, at the value of xn you have g of xn equal to 0, so this term will go to 0. So now you will, from this you can write as xn can be written in terms of xn minus 1 minus xn minus 1 minus g of xn minus 1 by g prime is the derivative of g of x at xn minus 1. So you will have xn equals xn minus 1 minus so the idea here is we start with an initial get x0 and from there we calculate the value of x1 so on, and then you iterate till your delta x is below certain tolerance or your g value, your value of g is below certain tolerance. So you can either have, you can specify your convergence criteria in two different ways, or maybe ideally you should specify both of them. Your value of g of x should be less than your tolerance. So this is the function tolerance, or if you are using MATLAB, this is what they call FL tolerance. And then you can also stop when your delta x, essentially your xn minus 1 is less than some tolerance. So what we mean by the first one is essentially you have reached your root, that is g of x equal to 0. By second one, what it means is the method is not able to improve any further, so any further iterations is not going to give you better results, so you'll just stop your iterations. So now how is this relevant to our particular problem? So wait, so this is our equation. So in this particular case, we have written equation just for a single cell, but eventually we will be writing equation for all the cells. So I would like to write it in a slightly different fashion, slightly different notation. What we are doing essentially, say, theta is your original variable, theta as a function of x. So what we are doing after discretization is essentially we are writing it as a vector theta bar, which is essentially theta 0, theta 1, and so on, theta n. Now this operation here is essentially del square theta by del x square, which, if you are familiar with finite difference, is your second derivative, can be represented using a differential operator d. So what d has is, d is something, is a matrix of n by n. What it does is essentially, or you can write d in a different way. So your D is essentially a matrix that contains your AP, A east and A west for all the cells. This will be your diagonal. Say I am just calling 0 as the main diagonal. This will be your super diagonal, say 1. This will be your one minor diagonal, so I am just calling minus 1. So 0 is your main diagonal, this is 1 and this is minus 1. So D is an operator which has its coefficients AP, A east and A west arranged in this particular manner. So if you multiply, so I am just using the notation of MATLAB. So this is indicator of matrix multiplication. So d times theta bar will essentially give you this expression. So we are using Crank and Coulson. So on the LHS we will be having theta bar calculated at say n plus 1 minus theta bar at n by delta t will be half. You have theta bar at n plus 1. Okay, we already taken half. Theta bar evaluated at n. So now this equation is again, if you write it as theta bar of n plus 1, is theta bar, the subscript here n and n plus 1 are essentially the time steps, plus you have a delta t over 2 differential operator, and then we also have so this is the known component and this is the unknown component. The objective here is to, we know the value of theta n bar, theta like this entire value is known, we need to find the value of theta bar n plus 1. So the only difference is this, if we write the previously whatever we discussed for Newton-Raphson, we write a new function g which is a function of n plus 1 as theta bar n plus 1, or we will write the original. Okay, we might not have to write this in this way, so we will take the original equation itself. So from this equation we can write g of theta bar of n plus 1 as I am just bringing that to LHS. So you have something like this, and our objective is essentially make this equal to 0, like find the value of theta bar of n plus 1 that will make this expression equal to 0. That is our objective. So to use Newton-Raphson, what we have to do here is a very simple thing. So we start with an initial guess theta bar of 0, and then what we do, how do we get theta bar of n is theta bar of 0 minus g prime of theta bar of 0. The only problem is what is the value of g prime. G prime is essentially, now we have here D is essentially a matrix of order n by n. So g prime is now what you call a Jacobian. This will be of size of order n by n. In our particular case, so now here theta bar and all of them are matrices. So how do I get g prime? It's again straightforward. So if you have to apply a derivative for this function over here, so instead of 1 over delta t times theta bar of n plus 1, now we will get a matrix here instead of 1, so that will be an identity matrix, and then theta bar of n is a constant, so you will have a 0 matrix, and then minus half times d is your operator, and then the last constant, the last one is a known one, so you don't have any derivative. So this is your Jacobian, g prime of theta bar of n. You already know the value of d. D is essentially your coefficients a, p, a east and a west arranged in this particular fashion, and I is an identity matrix. So from there you will get the value of Jacobian. Once you get the Jacobian, so I am denoting it with j is my Jacobian. J times d theta bar or delta theta bar will be minus g of theta bar. Delta theta bar is essentially 1 minus 0. So once you get now this equation here is again this is of the form Ax equal to b. So this is a linear equation. So if you see here, what does j have? J is essentially 1 by delta t times I minus half times d. So d essentially have only 3, this is a tridiagonal matrix. Your I is just a diagonal matrix. So if you subtract a tridiagonal matrix from a diagonal matrix, you will be ending up with another tridiagonal matrix. So J is essentially a tridiagonal matrix. So you have Ax equal to b, where A is a tridiagonal matrix. So you can solve this linear equation using TDMA. So this can be solved using TDMA. to get your values of delta theta. Once you get the value of delta theta, you can get the value of theta 1. You take the previous guess value, minus, okay, if you put a plus here, it will be of x plus b, so then you can just take this. So theta 1 will be theta 2 minus, I just remove the minus here and can write it in this way. So theta 1 bar will be the previous value minus this. Now you keep on iterating this till the norm, you can take an L2 norm as your convergence criteria. So convergence criteria can be written as A of theta bar at whatever step n, say L2 norm is within the tolerance, or you can also take in terms of delta theta is less than some tolerance. This will be your convergence criteria. You can take any one of them or both of them. I think the idea is clear. Actually thought of going through a code so that you will be more familiar with it. Yeah, so n is your number of cells, so I'm just considering 100 cells. Alpha and L, like we don't have any diffusivity and length, so I'm just considering both of them to be 1. And time step, I'm considering a value of 0.01. Theta 0 is my initial guess, so I have to give an initial guess of a linear profile, which I'll do later. And theta is just a variable to store all the values along x and time. The coefficients, in our particular case, A west is always 1 over delta x square, A east is 1 over delta x square. B, we don't have any source term here, and then AP is 2 over delta x square. So essentially this we have a 1 over delta x coming from the d theta dx, and then on the LHS we have dou theta dou t into a delta x. So that delta x, if you bring to the RHS, we'll have a delta x square. So these coefficients are done. So what I am doing here is we are explicitly specifying the Jacobian. So this is called an analytical Jacobian. So if you are familiar with MATLAB, it does offer you functions to evaluate Jacobian numerically. Alternatively, you can also provide an analytical Jacobian. So for those of you who are familiar with MATLAB, you have an option to give Jacobian yourself. That will essentially reduce your computation cost. So a Jacobian is an n by n matrix, so you need to perform order of n square, but in our particular problem we know that this is a tridiagonal matrix, so you'll essentially have 3n elements to calculate. So your computation will be reduced from order of n square to order of n if you actually provide the Jacobian. This function is just to calculate the norm. The TDMA algorithm is again straightforward. So we have this PQ, and phi is your final solution. So you have P0, Q0 defined, and then you iterate to get the values of Pi, Qi. And once the iteration is done, you take the last value to be equal to Q, and then we just iterate from last cell to the first cell to get all the values of Phi. So this is essentially to calculate the RHS we have on our equation. So the RHS is again A west times y minus plus A east times yi plus 1 plus Pi minus AP of yi minus 1. This is the spatial component. So now G is the function that I defined, where we have this is my d theta by dt term minus you have half of RHS1 is essentially the spatial derivative evaluated at n plus 1 step, and 0 is evaluated at the nth step. So now the problem is we don't know the value of n plus 1 step. So we start with an initial guess and then we kind of iterate it. So we need to use a iterative algorithm, that is your Newton-Raphson method. So implementation of Newton-Raphson is again straightforward. You give a tolerance, and if your error I am calculating here as a norm of it, norm of the delta theta. So to solve the equation j times delta theta equal to g, I am using TDMA again. So our traditional TDMA algorithm needs your coefficient in this way. So JAP is your diagonal elements, JA east is your super diagonal, and JA is your subdiagonal, and Gval is essentially the value of function G that is evaluated at that particular that has both RHS1 and RHS2. So that is this expression over here. So if you see here, I have defined the boundaries. So at the boundaries on the LHS we have a Dirichlet condition, so AP gets incremented by 1, and on the RHS we have a Neumann condition, so it gets decremented by 1. So to get the Jacobian values, how do we get the Jacobian values here? This term is on the LHS, and you have this half coming because of using a Crank-Nicolson scheme. So if it is a fully implicit method, you would have a 1 here instead of half. If it is a fully explicit method, you don't have any of these terms, or like you don't have any off diagonal components, so this will be 0. So this is f that the professor will be speaking in the lectures. So once you update these Jacobian values, so TDMA will be able to solve it. So, and I'll just show you the solution. So this is the solution I get once I solve the system of equations. So x-axis is my position, and y-axis is my time. So after a time of around 0.2 seconds, you see here at x equal to 1, that is my rightmost end. Initially the values are close to 1, so since it is an adiabatic tip, so but eventually the values will keep on reducing since we don't have any source term, it gets just spread out. So the question asks you to solve till this end value is equal to 0.5, so I've just stopped iterations after that. So you can keep on iterating till eventually this end temperature will go to 0. I think this is clear. Are there any questions in the implementation?
No, it's fine.
Yeah, thank you. So we'll come to the last question. This is where we kind of ended in the last session as well. So we have a 1D unstudied diffusion equation, but this is in a spherical coordinate system. So however, I've just introduced one more thing. So the previous question is also 1D unstudied equation, but then we have a constant diffusivity. The thermal conductivity is a constant there, but here what I'm saying is this thermal conductivity is also a function of concentration. So how do we approach this problem? So my diffusivity here is a function of concentration. Initially at t equal to 0, the concentration is C0 throughout the domain, and then at the center we have 0, and on the extreme, so I'm just saying J is some constant. This is my R equal to 0. Yeah, but before that maybe we should go through the question. So the first part is essentially to discretize the equation and then get the expressions for east, west, AP and B, assuming it is a steady state. We need to write the boundary equations, and then we need to state what is the accuracy of the discretization we have done. Once you define this, the D part asks you to calculate the value of C at the outer boundary. The next part goes to an unsteady case, and then finally we will solve using Crank-Nicolson. The algorithm is again anyway clear right now, so it should be straightforward for the last part. So if we can come up to this, it will be good. So for an unsteady part, I think it is straightforward. The only thing I want to point out here is when you have this, until now what we are doing is when we have fluxes on these cells, we start with considering the phases, and then we will take the nodes. So our unknowns are essentially the values at the nodes. Say this is my Cn minus 1. So what I have for the last cell. This is my Cn minus 1, the value of C at the n minus 1 node, and this is my face value. This is my east boundary. How do I calculate the value at this particular east boundary if I know the value of Cn minus 1? Like, this is one way of discretizing your domain. Now if you go in a different way, we can consider r equal to 0 and r equal to r as our nodes, and then we discretize the domain in this way. So essentially what we have here is just a half cell, the other half is just fictitious, this other half is just fictitious, and remaining everything is similar. So essentially your ends, I can consider them as unknowns and assume something like this, or I can go in this particular fashion. So if I do in this way, then I would directly get the value on the east boundary, since that is an unknown included in the equation. So when you write a set of equations, your node value is user unknown. So now you can write your boundary points as unknowns and you will get these equations. So that is one way. The other way is the standard way now we are following for all the problems we are solving. So we consider only the faces. So what do you think so if we go in the way we are approaching till now, so we will be approaching this way. So how do we get the value on the east boundary if I know the value of n minus 1 cell? That is one part I would like to address, so maybe we will take it up. So the first question asks you to essentially discretize the cell, so we will do that. So assuming it is steady process. So times dv is essentially 4 pi r square dr equals to 0. So this is my peach cell, so west and east face. So this is, I think by now it should be standard. So your r square gets cancelled and 4 pi will be 0. So you'll be left with r square d del c del r aggregated on the east face minus r square d del c del r evaluated on the west face equal to 0. So this is r east square times d of c east del c del r on the east face is c east minus cp delta r minus r west square d of c west so like as we have previously discussed, this type of linearization is of order delta r square. So it's a second order accurate profile. So the problem is we don't know the value of c little e and c little w. Like r east and r west are known. So r east will be essentially rp plus, if you assume a uniform grid, it will be delta r by 2, and r west is again straightforward, so it will be rp minus delta r by 2. The only unknowns are c little e and cw. So it's like previously, we will just start again with a linear approximation. So your c little e, we will just take it as the mean value. Sorry. And then your c little w can be written as cp plus c west by 2. Once you take these approximations, you substitute back in c little e and e, and you will get an equation here. So I can write the above equations as a east c east plus a west c west minus ap cp equals 0, where your a east is essentially r little e square d of c the r, a west is square d of cw, and your AP is essentially A east plus A west. So this is straightforward. The only catch here is you just need to approximate this to get the value of on the faces, on the face centroids as mean of the cell centroid values. So now that we know the values of AP and A west, the order of accuracy is already order of delta square. So now how do we get the boundary value? So this is the question we asked in the first place. So the second part essentially asks you to write equations for the boundary cells. So we'll take the left boundary. My west boundary. This is my 0 cell. This is my first cell. So since it is for the west boundary, so you have AW equals 0. Your A wish will be same as the previous case. So you have R little e. So this is straightforward. So how will this change? So it is a delta x by 2. So now your AP will have essentially what, when we write the equation, it will be R e square d del c del r on the east face minus the boundary condition essentially says this is equal to 0. So you don't have any contribution from the west term. So AP equals to A east. However, on the right boundary, this is my n minus 1, this is my n minus 2. On the right boundary, your A east will be 0, your A west will be the same, but your AP will now have since your del CDR value R e square times d of C east into del C del R on the east face will be essentially equal to minus R east will be equal to J. So that is the boundary condition that is specified. So this is essentially a constant. So this will go to your B term and your AP will be equal to AW. Since it is a normal condition, you won't have any contributions to your AP term. So now that you have all the coefficients of AP and AW, that is essentially the next part of the question. So it asks you to write for the boundary cases. Order of accuracy, as we have seen, it is delta R square. The fourth question asks you to derive expression for the value at R equal to R. So now we have del C del R. C is essentially order of delta R square. Our objective is to find the value of C at the value at the surface at R equal to capital R. So how do I get this? So this is at R equal to R. I know the value of Cn minus 1 and this is essentially delta R by 2. So one way is to directly use the boundary condition. So your boundary condition is d times del C del R at the value of R at R equal to capital R equals to J. So what we can do is write this del C del R as C evaluated at R equal to R minus Cn minus 1 by delta R over 2 equals J. So from this you can get the value for at R equals to R, can be written as Cn minus 1 2D. The question is, what will be the order of accuracy with this approximation? So what I am doing essentially here, C at R equal to R is being now written in terms of Cn minus 1 plus, or maybe I should say minus. It's like if we do the Taylor series approximation, Cn minus 1 will correspond to essentially C evaluated at R minus delta R by 2. So if I just do a Taylor series expansion, C at r equal to r can be written as Cn minus 1 plus delta r by 2 del C del r, or okay, I should write it in a different way. Right, Cn minus 1 can be written as C at r equal to r minus delta r by 2 del C del r so plus some second order. So what we are doing now, we are replacing C at r equal to r with Cn minus 1. So this is essentially if you equal this in terms of j and this. So if you compare this equation and this equation, so the approximation we have taken is the order of delta r square, and our original approximation, our original equation will also be in the form of discretized equation, is also of the second order. So it is of same order, so it wouldn't be a much of an issue. Alternatively, you can also use a different approach, slightly different, but still that will also give you a second order. So I want to find C at r equal to r, and I know the value of Cn minus 1, and if this is my Cn minus 2, so I know both Cn minus 1 and Cn minus 2, both are second order accurate. So I can just use a linear combination of them to determine the value of this. So essentially I have this as delta r and this is delta r by 2. So I can write this as Cn minus 1 minus Cn minus 2 by delta r to be equal to r minus, if I just use a linear approximation, so that would give me C at r equals to r equals 2 times Cn minus 1 minus Cn minus 2 by 2. So since this and this both are second order accurate, this will also be of the second order accuracy. So this is another way to calculate your surface value. Like you can come up with different combinations, even then, like this is one way, and to get even more accurate, the only difference is the, like both are second order accurate. The second, what I mean by second order accuracy is if you refine your mesh, it will get converged in that way. But the original question is what will be the accuracy of say this is equation 1 and this is equation 2. Which one of these do you think will be more accurate in terms of representing the actual value? It appears that equation 2 is more accurate compared to equation 1. So when you try to compare with more refined solutions, equation 2 is found to give more accurate results than equation 1. The idea here is, in order to determine the value at the boundary, you are just using one cell. Instead, if we use more cells, we will get more information. More information will be incorporated into it, so that it will be more accurate compared to the other ones. So you can expand the idea to more number of cells. Say instead of just taking 2 cells, say to determine the boundary cell, instead of just taking the n minus 1 or n minus 2, we can take an average of all the cells, weighed accordingly. Like here we have just taken n minus 1 and n minus 2 cell, but instead you can take all the cells, say from Ci, where I equal to 0 to n minus 1. You can take all the cells and then take some weighted average and then come up with an expression for this. However, the expression will still be order of delta r square, but it will be more accurate compared to this one. So accuracy is different from your convergence. So I hope that is clear. Let's solve this part. So now we come to the unstudy part. So the LHS is again straightforward. So we have del C del T. Now if you were to integrate this, so we would be taking 4 pi r. I'm just removing the 4 pi since it will be cancelled with the RHS side. So r square dr will be equal to this entire RHS term you are having. The RHS term is essentially something like A west, C west, APCP. I am just writing this as some f of C bar, where this C bar, like previously what we have seen, C is your original vector. Now what we have done, we have discretized it to get C bar. C bar will essentially have, it's a vector C0, C1, so on. You have Cn minus 1. So this is essentially your vector. So if you are solving using some MATLAB or something, you will be writing all your variables in terms of vectors. So how do I solve this? We just take the time derivative outside. So you have r square C dr. This can be written as rp square Cp delta r will be equal to f of C bar. So the question asks you to formulate in a different way. So you have m times del C bar del T, where m is essentially your rp square times Cp matrix, or write in the indicial form, it will be like, since it is a matrix, I am writing in the indicial form. So Ra square Ci, so that will be something like R0 square C0, so on, 0 R1 square C1, so this will be 0 0 R2 square C2, and so on. So this will be your M matrix times dc dt equals f of C bar. C bar is essentially this vector. Now the question is, how do I solve this equation? Is f of C bar. So to solve this kind of equations, again we will have to use some discretization in the time domain. So if you were to use an Euler or an explicit method, explicit is straightforward, so we'll start with that. So the idea is very simple. So you have C bar evaluated at n plus 1, C bar by delta t, it's f of C bar evaluated at n. So you have m over delta t, C bar n plus 1 equals so this particular equation is of the form A times C bar equal to B. So you know the value of A and B, and this is a diagonal matrix, so which essentially simplifies your problem even further. So once you evaluate the values of B, you can get the values of C bar at that particular time step at n plus 1, and you can keep on marching in time till you reach your steady state or whatever will be your condition depending on your problem. The problem gets complicated if you were to use, say, Crank-Nicolson. Say if I have to use Crank-Nicolson, LHS will be similar, Cn plus 1 minus Cn by delta t. In the RHS you will have contributions from the current time step and the next time step. So the approach is very similar. Now you define a function g, which is n plus 1, something as just take to the LHS. The problem again here is how do you evaluate the value of Jacobian. So essentially what I mean is say del G by del C bar. Your G is essentially a matrix of order n by 1. Your C bar is essentially another matrix, another vector, or say both are vectors. So your Jacobian, if I denote it by J, will be of order n by n. How do I evaluate this particular matrix? Any ideas, or have you already come across such methods to calculate Jacobians?
No, this is the first.
Okay. Then maybe I should show some. So this is some particular paper to derive the analytical Jacobians. The idea is like you have certain rules that you have to follow when you are doing derivatives with respect to vectors. It's like this will be very similar to how you do for a scalar. So the notation is, this is for matrix multiplication. It's like this notation is very similar to MATLAB for those of you who are using MATLAB, and dot times this is the head-amount product, or you multiply element-wise multiplication. So the product rule is simple. So if you have a matrix operator operating on u hat, so that will just give you the matrix. So this is something like A is some constant, and so like it's very similar to your scalar multiplication. The diagonal rule tells you, so f of u hat is some vector where f is a function operating on it's an element wise function. So what I mean by element wise function is, say your u hat is xy and f of u hat is some square function or something. So what I mean is this will give you x square y square. So it does this particular operation on each and every element. In that particular case, f of u hat will again be a vector, u hat will also be a vector. So if you want to apply derivative of this with respect to this, the operation is something like this. It's like it's quite straightforward. Things get complicated when, okay, sorry, it's actually diagonal. So just to give you an idea, so you have your u hat as xy and f is a function that is a square function. So f of u hat will give you x square y square. So my objective is to calculate del f by del u hat. So what it gives you is x of x square it's like with respect to each component you apply on the first derivatives, and then you have del x on the second one, so y square. So this is something like your Hessian matrix that you might be aware in your mathematics course. So this will essentially give you 2x 0 0 2y. So this I am writing as diagonal of f prime of u hat. So essentially f prime of u hat, if you directly apply the derivative here, so that will essentially give you 2x 2y. So this is equal to this. That is your diagonal rule. And you have some chain rules. These are again very similar to the normal ones we will be using it. So you have an operator operating on some function, so you just take the operator out and you have derivative with respect to, since a is not a function of u hat. Now if you have a function operating on this, then you take the derivative, evaluate it at that value times that particular operator comes outside. And the most important one that we will be using now for this particular problem is the product rule. Now here you have an operator, f and g are two different operators. So when I am doing this, this is an element wise multiplication. So it's something like if you have f of u hat as say xy and g of u hat as say x square y square. What I mean by element wise multiplication is something like dot star g of u hat is you just take x times x square and y times y square. So this is the operation you will get if you do dot star. So that is this particular operation. When you have something of this sort, you can kind of treat these as your identities that you will be using now to evaluate your Jacobian. Maybe I'll show one simple example here. Sorry. So in our particular case, what is my f of c prime? So if I see this is my f of c prime, so what we have is a west c west plus a c east minus apcp. So like we have seen previously, like this thing will essentially give you a diagonal, super diagonal and subdiagonal. So essentially you can write this as some operator d operating on your c. You can write it in this particular way. The problem is this is something we have done for the previous problem also, like we expressed the RHS in terms of some differential operator times c bar. The only problem with the previous one and the current one is previously the coefficients are not functions of your c, but in the present case your a west, if you see the expression for a west, I think I have written somewhere, yeah, so the expression for a east has a contribution from c east and west also has a contribution from c west. So your coefficients will change as a function of both space and time. So like they are dependent on your concentration, which is again dependent on your space and time. So this differential operator here is not a constant but a function of c bar. So I cannot write it in this way, so I need to kind of understand how do I actually get the terms inside D. So we'll just take one expression to, maybe we'll take a west to just show you how it is. So if a west is essentially having r west square d of c west, okay, maybe I should use different operators here. So d here stands for diffusivity. Say I am using some different operator, something like this, where this is some differential operator times delta r. So d is essentially the diffusivity function. Here d is your diffusivity. Now I am trying to replace c bar, so r west can be written as rp minus delta r by 2 times so instead of rp I am just writing as r bar times your d is your diffusivity function and Cw is essentially your west phase, that is kind of written as Cp plus C west by 2. So I can kind of come up with a matrix capital A times C bar, where A can be written as, it has contributions from the west coefficient and the current coefficient. So you can write it in this particular way, where you have, so it's actually 0.5 from the west one and 0.5 from the current phase. So you have 0 everywhere. Similarly 0, 0.5, 0.5, 0 and so on till the last cell you have 1. So if I write it in this particular way, A as something like this, when you operate this on your C, C0, C1 so on, any particular value for that particular cell will essentially give you, say we are taking this particular law, you will have a value of C0 by 2 plus C1 by 2 for the first cell. So what I am trying to do is I am just trying to write everything in a matrix format so that you will be able to use identities we have defined previously. So this is one term which is the kind of expression in terms of R. So I am writing this say as B, this entire term as B times, B is a vector, so we are multiplying each term, so it should be head-amount product or element wise multiplication. D is a function, so you just write D of and this is a normal one. So you have something of this sort. Now the idea is you have f of c bar, So if you see del G del C, so this is our G. So to evaluate the value of del G at del C bar, the first one is straightforward. So you have a matrix times this, so you just get the matrix here, minus half del F by del C bar. So I would be needing the value of del F by del C bar, and it will be F will be something of this form, like I have seen. So F will be something of some matrix B times diffusivity of A times C bar. So now we need to find del F by del C bar. So we'll use the same formulas that I have shown previously. So I have a Harriman product of A times C star. So the first rule is we use a product rule. So that is essentially tells its diagonal of d of A times C bar so just to show you, so we will be using this particular form, product rule. So we have some function of u hat times another one, so it will essentially be split into two parts. That's the same expression I am using now, plus you have diagonal of B times del C of d of A times C bar. So now B is essentially some constant which is only depending on your location, it doesn't change here, so this particular term goes to 0. So now you are left with diag of B times, now again here we have to use this particular form. So del u hat of f of u hat, instead of f we are now having diffusivity as a function of C bar, so it will be this, we just use it. So we'll be left with diagonal of d prime of A times C bar times instead of C bar you have coefficient of A, so this just comes out times A. So this is essentially your del F by del C bar. So now you know the value of this and this, so if you substitute back you can get the value of del C bar. So this will be your Jacobian matrix. So from here it will be again straightforward. Once you know the Jacobian matrix, so the equation will be something like del times del C bar equal to Z, and from this you solve this equation using, say even in this particular case the matrices are your B matrix, your D, and all of these will be at most like you'll have tridiagonal matrices, and most of the time your A matrix is essentially have either super diagonal or the subdiagonal. It doesn't have both of them, and your diffusivity is just a function. Your B matrix is again a diagonal matrix like we have seen previously. So B is essentially R square, so that will only depend on that particular Ri value, and the previous and the corresponding values will be, next values will be 0. So this will again you can solve using TDMA. So once you get the value of delta C bar, you can get the value of C bar n plus 1 in terms of C bar n minus delta C bar. This is the next time step, and then you keep on iterating till your whatever convergence criteria is there. Is this clear, or have any queries? Yeah, but this.
I will go through the recorded video once and get back to you.
Yeah, sure. So if you have any queries, you can refer to this paper by 2009 on analytical Jacobians. So I'll share this as well, so that you can go through it. You can come back in the next session as well. The other way is, instead of doing it in an analytical way, you can do it in a numerical way. It's very crude, but still you can do it in that way. The idea is your Jacobian can be calculated as g of you just increment you say The idea is simple. So your objective is to determine f of x, f prime of x. You just use the normal form. So what we do, within your tolerance, you will specify a known delta x. Say you already know the value of xn minus 1. So you specify a given value of delta x, and for the delta x you can calculate, since the value of function is known, you can get the value of f of x and use this approximation to get f prime of x. The only problem is you need to kind of, it will be of order of n square. Since you have n square components, you need to do it for each and every individual. So like x is not a scalar here, you have a vector, so you need to do this for all the combinations. Like what I meant is, you have two vectors, you have f is one vector and u is one vector. So f is a vector of say f1, f2 and so on, fn, and u is another vector, or in our case c is the vector, so c1, c2 and so on, cn. So to calculate your Jacobian, what you have to do is, it's something like del f1 by del c1, 1 by del c2 and so on. Similarly, so it is something like this, and each of these things can be approximated using this. So say del f1 by del cn, what you do is, you just increment the value of that particular cn by delta c, and then you will evaluate f of n. So all other coefficients remain the same, only cn will be incremented by say delta c, minus everything is remaining the same by delta c. That will give you the value of that particular element in your Jacobian. Now this has to be done for all the values to get your entire Jacobian matrix. Like, this is a crude way, but this can also be done. This is something that is by default implemented in your MATLAB in a more stable way. I don't remember the function, but it is something called numjac or something, numerical Jacobian or something. You can do it in a numerical way to estimate your Jacobian and use it, but it will be computationally more expensive compared to this analytical one. We have 2 minutes left. Maybe I'll just brief you about the other case. So we started out taking in this particular form, but however we can take the second approach as well. You can actually try solving it using second approach. What if I consider cell node at the boundaries? Instead of taking the face at this, I can take this as my center nodes, both the boundaries as my cell centers, and take a half cell. And if I do in that particular way, I will directly get the value of C at r equal to r instead of any approximations that we have done. So what do you think? Do you have any problem? Maybe you can try doing in this particular way. Maybe we can discuss in the next class. So if you get any problems or it just works fine. So why should we use the other method, or when should we use the first method, and when should we use this particular approach? I think we are almost out of time, so maybe we'll discuss in the next session. I think the question is clear. So what I essentially wanted to ask is, instead of considering the face centers, we discretize in this particular way, then we can directly get the value of C at r equal to r instead of approximating it like we have done. So which of these two methods will you think will give you a better or accurate result for C at r equal to r, or both is the question. Yeah, we'll take that up in the next session. Thank you all.
Thank you.